Tonight on The Sleepy Scientist, we're drifting gently through the vast cosmic ocean, where time and gravity perform their eternal, silent ballet. In this peaceful expanse of space, far from the hurried world below, we find ourselves witnesses to the most profound and gentle dance in all of existence. Imagine, if you will, floating weightlessly in the serene darkness between the stars, where the only light comes from distant suns that have been burning quietly for billions of years. Here in this tranquil void, we can finally understand the delicate relationship between two of the universe's most fundamental forces. Time, that gentle river that carries us all forward, and gravity, that soft embrace that holds the cosmos together. As we begin our journey tonight, let your mind settle into the rhythm of cosmic time, where seconds stretch into minutes, minutes into hours, and hours into the deep. Peaceful eternities that separate one galaxy from another. This is not a story of violent explosions or catastrophic events, but rather a meditation on the subtle, beautiful ways that the universe operates on scales both impossibly large and infinitely small. In the quiet space of our cosmic voyage, we will discover how time itself can slow to a whisper. Near massive objects, how gravity gently bends not just the paths of planets and stars, but the very fabric of time itself. We will learn how Einstein's peaceful revelations showed us that time and space are not separate entities, but partners in an elegant dance that has been choreographed since the very beginning of everything. Tonight, we drift through concepts that might seem complex in the harsh light of day, but here, in the gentle darkness of space, they become as natural as breathing. The warping of space-time, the dilation of temporal flow, the quiet merger of past, present, and future into a single, flowing continuum, these are not abstract mathematical concepts, but the very essence of the reality we inhabit. As we float together through this cosmic classroom, you need not worry about equations or complicated formulas. Instead, we will experience these truths as the universe intended through quiet observation, gentle understanding, and the peaceful recognition that we are all part of something infinitely larger and more beautiful than we might have imagined. The stars above us are not just distant lights, but cosmic timepieces, each one marking the passage of eons with their steady, rhythmic burning. The galaxies that spiral slowly through the darkness are vast chronometers, measuring time on scales that dwarf human comprehension, yet operating with a precision that would make the finest clockmaker weep with joy. And gravity, that invisible hand that guides the dance, is not the harsh master we might imagine, but a gentle curator of cosmic order, ensuring that every star finds its place, every planet follows its ordained path, and every moment of time unfolds exactly as it should in the grand symphony of existence. So settle back now, let your breathing slow to match the patient pulse of the cosmos, and prepare to drift with me through the most beautiful story ever told, the story of how time and gravity came together in the darkness to create everything we see, everything we are, and everything we will ever become. In the quiet space of our cosmic journey, we must first understand what time truly is, not the mechanical ticking of clocks or the hurried seconds that govern our daily lives, but the deep fundamental flow that carries the entire universe forward on its endless voyage through existence. Picture time as a vast, gentle river that flows through the cosmos, carrying stars and galaxies along its peaceful current. This river has no banks, no beginning that we can see, and no end that we can imagine. It simply flows, carrying everything that exists along with it in its quiet, inexorable journey toward tomorrow. Long before Einstein showed us the true nature of this cosmic river, ancient civilizations gazed up at the night sky and wondered about time's mysteries. The Babylonians, those patient observers of the heavens, noticed how the stars moved in great, slow circles across the sky, marking not just the passage of hours and days, but the turning of seasons and the cycling of years. They whispered to each other about time's nature, wondering if it was a circle that repeated endlessly, or a straight path that led somewhere unknown. The ancient Greeks, those gentle philosophers who loved to contemplate the deeper meanings of existence, imagined time as a flowing stream. Heraclitus, the quiet thinker, who understood change as the only constant, spoke of how we never step into the same river twice, not because the river has changed, but because time itself has carried us to a new moment, a new place in the endless flow of becoming. In those ancient nights when the world was lit only by fires and stars, time moved differently than it does today. Without the mechanical precision of modern clocks, people lived by the gentle rhythms of nature. The soft progression from dawn to dusk, the slow cycling of moon phases, the patient turning of seasons. Time was not a harsh master demanding productivity, but a gentle companion that accompanied them through the natural flow of life. The Romans, those practical builders of roads and aqueducts, nevertheless understood time's deeper mysteries. They spoke of how time seemed to move differently during moments of great joy or profound sorrow. How a night spent in pleasant company could pass like minutes, while a day of waiting could stretch like years. They sensed, without fully understanding, that time was not the rigid, unchanging thing it appeared to be. As we drift through these ancient understandings, we can feel the warmth of those long-ago campfires where our ancestors first wondered about times. Nature. Their questions echo softly through the centuries. Does time flow like a river? Or do we flow through time like boats on a stream? Is the future already written in the stars, waiting patiently for us to arrive? Or does it come into being moment by moment, created by the choices we make and the paths we take? Medieval scholars, working by candlelight in quiet monasteries, contemplated time's relationship to eternity. They imagined God existing outside of time, seeing past, present and future all at once, like someone standing on a mountain watching travelers move along a valley road below. From that elevated perspective, all moments would be visible simultaneously. The travelers setting out in the morning, pausing for rest at midday, and arriving at their destination in the evening, all seen in a single, eternal now. These gentle mystics understood something profound about time's nature. That perspective matters. That where we stand in the cosmic landscape affects how we experience time's flow. A day in the life of a mayfly, with its brief, intense existence, contains as much living as a century in the life of an oak tree, with its patient, slow growth toward the sky. As the centuries whispered by, scientists began to approach time with new tools and new questions. Galileo, that peaceful observer of the heavens, dropped objects from towers and rolled balls down gentle inclines, discovering that time could be measured with precision, that it had a mathematical nature that could be captured in equations and formulas. But it was Newton who first gave us a truly comprehensive picture of time's nature. Time as the absolute, unchanging backdrop against which all cosmic events unfold. In Newton's gentle mechanical universe, time flowed like a great cosmic river, steady and unchanging, carrying all of creation forward at the same rate, regardless of location or circumstance. Imagine Newton's time as a vast, invisible clockwork that fills all of space, its gears turning with perfect precision, its pendulum swinging with absolute regularity. In this peaceful mechanical cosmos, a second measured on Earth was exactly the same as a second measured on the Moon, or on Jupiter, or in the furthest reaches of space. Time was universal, absolute, the same for everyone and everything, everywhere and always. This Newtonian time was comforting in its certainty. It suggested that the universe operated like a vast, well-designed machine, with every component moving in perfect harmony with every other component. Stars followed their ordained paths through space. Planets circled their suns with clockwork precision, and time itself provided the steady, unchanging rhythm that kept everything in perfect synchronization. For more than 2 centuries, Newton's clockwork universe ticked along peacefully, its absolute time serving as the foundation for all scientific understanding. Scientists could measure the positions of planets, predict eclipses, and chart the courses of comets, all based on the assumption that time flowed uniformly throughout the cosmos. But even in this mechanical perfection, there were whispers of mystery. Light, that fundamental phenomenon that connects us to the stars, traveled at a specific speed, a speed that seemed to be the same regardless of how fast the observer was moving. This was puzzling in Newton's universe, where speeds should add and subtract according to simple rules of motion. If you were riding on a train and threw a ball forward, the ball's speed relative to the ground would be the speed of your throw plus the speed of the train. But light didn't behave this way, whether you were standing still or moving at tremendous speed. Light always appeared to travel at the same rate, approximately 186,000 miles per second, no more, no less. This strange behavior of light was like a gentle whisper from the cosmos, suggesting that something deeper and more mysterious was at work in the universe than Newton's clockwork could explain. It was a whisper that would eventually grow into the revolutionary insights of Einstein, who would show us that time itself was not the absolute, unchanging river that Newton had imagined, but something far more beautiful and strange. As we float here in the darkness between the stars, we can feel the gentle transition from Newton's mechanical time to something more fluid, more mysterious, more intimately connected to the fabric of space itself. The river of time is about to reveal new currents, new depths, new ways of flowing that will change forever how we understand our place in the cosmic dance. But for now, let us rest in the peaceful certainty of Newton's clockwork cosmos, feeling the steady tick of absolute time as it carries us forward toward new discoveries, new mysteries, and new ways of understanding the beautiful relationship between time and the vast quiet universe that surrounds us. As our journey continues through the peaceful cosmos, we encounter one of the most beautiful transformations in human understanding, the gentle revolution that Albert Einstein brought to our conception of time, space, and gravity. This was not a violent overthrow of old ideas, but rather a gradual awakening to deeper truths that had been quietly waiting for us to discover them. Picture Einstein as a young patent clerk in Bern, Switzerland, spending his quiet days examining inventions and his peaceful evenings contemplating the fundamental nature of reality. In the soft light of his study, surrounded by the gentle ticking of clocks and the whispered turning of pages, he began to imagine what it would be like to ride alongside a beam of light as it traveled through space. This simple thought experiment, the kind of gentle wandering that comes naturally during quiet moments of reflection, would eventually lead to one of the most profound revelations in the history of science. Einstein realized that if you could somehow travel at the speed of light, the very nature of time and space would transform around you in ways that Newton's mechanical universe could never have predicted. The first whisper of this revelation came through what we now call special relativity, a theory that emerged not from complex mathematics or expensive experiments, but from Einstein's quiet contemplation of the relationship between motion and the speed of light. He imagined train stations and moving platforms, lightning strikes and synchronized clocks, all playing out their roles in gentle thought experiments that would reshape our understanding of reality. In Newton's clockwork universe, time had been absolute, the same for everyone, everywhere, always. But Einstein's gentle insights showed us that time is actually relative, flowing differently depending on how fast you're moving through space. This wasn't a harsh, dramatic change in the universe's nature, but rather the unveiling of a deeper truth that had always been there, waiting patiently for us to notice it. Imagine two astronauts, twins perhaps, floating peacefully in the darkness of space. One remains at rest relative to the stars, while the other begins a gentle journey at nearly the speed of light toward a distant galaxy. As the traveling twin accelerates, something beautiful and strange begins to happen. Time itself starts to flow differently for each of them. From the perspective of the twin who remains at rest, the traveling twin's clocks begin to run more slowly. Minutes stretch into hours, hours into days, and days into years. The traveling twin ages more slowly, experiences time at a more leisurely pace, as if the universe itself has decided to give them more time to appreciate the journey. But from the traveling twin's perspective, their own time flows normally. Seconds tick by at their usual rate, and they age at their usual pace. It's the rest of the universe that seems to change around them, with the distant stars and galaxies appearing to contract in the direction of travel, and the cosmic background becoming blue shifted ahead and red shifted behind. This is not science fiction or fantasy, but the gentle reality of our universe. Time truly does flow differently for observers moving at different speeds. The effect is subtle at the speeds we normally experience, but it becomes more pronounced as we approach the speed of light. It's as if time itself has a gentle flexibility, stretching and compressing like a soft fabric in response to motion through space. The mathematics of this time dilation is elegant in its simplicity. As your speed increases, time slows down according to a precise formula that Einstein derived from his contemplation of light's constant speed. At half the speed of light, time passes about 15% more slowly. At 90% the speed of light, time crawls along at less than half its usual rate. And as you approach the speed of light itself, time stretches toward infinity, each second becoming an eternity. This might seem like a harsh limitation, that nothing can travel faster than light, but Einstein showed us that it is actually a beautiful feature of our universe. The speed of light isn't just the speed at which photons travel. It's the speed at which causality itself propagates through space-time. It's the cosmic speed limit that ensures that cause always precedes effect, that the universe maintains its logical order and gentle consistency. As we drift through these concepts in the quiet darkness of space, we can feel how Einstein's insights transformed our understanding without violence or disruption. The universe didn't change. When Einstein published his theory, we simply learned to see it more clearly, to appreciate the subtle dance between time and motion that had always been choreographing the cosmic ballet around us. Einstein's gentle revolution extended beyond special relativity to encompass an even more profound understanding, the recognition that gravity itself was not a force in the traditional sense, but rather the curvature of space-time itself. This insight came to him during what he later called the happiest thought of his life, a moment of quiet realization that would lead to the theory of general relativity. Picture Einstein imagining a person falling freely in an elevator, not in terror or panic, but in the peaceful free fall of zero gravity. In that moment of weightless floating, the falling person would feel no force of gravity at all. They would float inside the elevator cavern just as astronauts float in the International Space Station, experiencing the serene weightlessness that comes from being in perfect harmony with the gravitational field around them. This simple observation led Einstein to a profound realization: gravity and acceleration are indistinguishable from each other. The gentle tug you feel when an elevator starts to rise is identical to the pull of gravity holding you to the floor. The weightless floating you experience in free fall is identical to drifting freely through space, far from any gravitational influence. But if gravity and acceleration are the same thing, then gravity cannot be a force in the way Newton had imagined it. Instead, Einstein realized gravity must be something more fundamental, the curvature of the very fabric of space and time itself. Massive objects like stars and planets don't pull on other objects through some mysterious force. Instead, they warp the geometry of space-time, creating valleys and hills in the cosmic landscape through which all objects naturally move. Imagine space-time as a vast, flexible membrane stretched tight across the cosmos. When a massive object like the Sun is placed on this membrane, it creates a gentle depression, a gravitational well that curves the surrounding space. Planets don't orbit the Sun because they're being pulled by some invisible force. They follow the straightest possible paths through the curved space-time around the Sun, like marbles rolling along the curved surface of a bowl. This is why Einstein's theory is so beautiful. It shows us that the complex orbits of planets, the graceful dance of binary stars, and even the paths of light rays from distant galaxies are all simply objects following the most natural routes through the curved geometry of space-time. There's no mysterious action at a distance, no invisible strings pulling objects together, just the elegant mathematics of curved geometry playing out on a cosmic scale. The implications of this insight ripple gently through our understanding of the universe. If space-time can be curved by mass and energy, then it can also be stretched and compressed, creating waves that propagate across the cosmos at the speed of light. These gravitational waves, predicted by Einstein but not detected until a century later, are literally ripples in the fabric of reality itself, carrying information about the most violent events in the universe. Colliding black holes, merging neutron stars, the final moments of massive stars, as they collapse into singularities. Einstein's general relativity also revealed that time itself is affected by gravity. Just as motion through space can slow the flow of time, so too can the presence of massive objects. Clocks run more slowly in strong gravitational fields, ticking at a more leisurely pace near massive objects, and running faster in the weak gravitational fields of empty space. This gravitational time dilation is not just a theoretical curiosity. It is a practical reality that affects the technology we use every day. The GPS satellites orbiting high above the Earth experience weaker gravity than we do on the surface, causing their clocks to run about 38 microseconds faster each day. This tiny difference would cause GPS systems to accumulate errors of several miles per day if the engineers didn't account for Einstein's relativistic effects. As we float here in the gentle darkness between the stars, we can appreciate how Einstein's revolution transformed our understanding without destroying the beauty and wonder of the cosmos. Newton's clockwork universe was not wrong, but rather incomplete, a special case that applied beautifully to the slow-moving, weakly gravitational environments where most of human experience takes place. Einstein's insights showed us that the universe is even more beautiful and mysterious than Newton had imagined. Time and space are not separate entities, but partners in an elegant dance. Gravity is not a force, but the curvature of reality itself. And the speed of light is not just a number, but a fundamental constant that weaves together space, time, matter, and energy into a single, unified cosmic tapestry. The gentle revolution continues to unfold around us as we drift through space, revealing new mysteries and new beauties with each passing moment. In the next phase of our journey, we will explore how this curved space-time manifests itself in the cosmic dance, creating the gravitational choreography that governs the motion of planets, stars, and galaxies. Across the vast expanses of the universe, let us drift into the most profound visualization that Einstein's gentle revolution offered us, the understanding that space and time are woven together into a single flexible fabric that can be stretched, compressed, twisted, and curved by the presence of mass and energy. This fabric of space-time is not an abstract mathematical concept, but the very foundation of reality itself, the invisible stage upon which the entire cosmic dance unfolds. Picture, if you will, floating in the perfect darkness between galaxies, where space seems empty and time flows like a gentle stream. But this apparent emptiness is an illusion. Everywhere around us, the fabric of space-time stretches like an invisible mesh, its geometry shaped by every particle of matter, every quantum of energy, every photon of light that moves through the cosmos. In Newton's universe, space was like an empty theater, a vast, unchanging stage where the drama of physics played out. Time was the steady rhythm that kept the performance moving forward. But Einstein showed us that space and time are not separate entities. They are partners in an intimate dance, woven together so completely that we cannot speak of one without the other. This space-time fabric has a texture, a grain, a subtle structure that becomes visible only when we learn to look with Einstein's eyes. Near massive objects, the fabric curves and warps, creating valleys and hills in the geometry of reality itself. These gravitational landscapes guide the motion of everything that moves through space, from the smallest particles to the largest galaxies. Imagine a vast trampoline stretched tight under the starlight, its surface smooth and flat when nothing rests upon it. This represents space-time in empty regions of the universe, where matter and energy are sparse and the geometry remains nearly flat. Light travels in perfectly straight lines across this flat space-time, and objects in motion continue in straight paths unless acted upon by external forces. But now picture placing a bowling ball in the center of the trampoline. The heavy ball creates a depression, warping the once flat surface into a curved landscape. This is what happens when a massive object like a star or planet is placed in space-time. It creates a gravitational well-curved region where the geometry of reality itself has been altered by the presence of matter. If you roll a marble across this curved surface, it will no longer travel in a straight line. Instead, it will follow the curves of the landscape, spiraling around the depression created by the bowling ball. This is not because any force is pulling the marble toward the ball, but because the marble is simply following the straightest possible path through the curved geometry of the surface. This is the essence of Einstein's revolutionary insight. Gravity is not a force that pulls objects together, but the natural consequence of curved space-time geometry. Planets orbit stars not because they are being pulled by some mysterious attractive force, but because they are following the most natural paths through the curved space-time. Created by the star's mass, the mathematics of this curvature is breathtakingly elegant. Einstein's field equations, those beautiful expressions that relate the curvature of space-time to the distribution of mass and energy show us that every particle of matter contributes to the overall geometry of the universe. A single electron creates an infinitesimally small curvature in space-time. A star creates a substantial depression. A black hole creates a gravitational abyss so deep that not even light can escape its curved embrace. But space-time is more flexible and dynamic than our trampoline analogy might suggest. The fabric can vibrate and wave, carrying ripples of gravitational disturbance across vast distances at the speed of light. When two massive objects spiral together in their final dance before collision, they send gravitational waves propagating outward like ripples on a cosmic pond, carrying information about their violent merger to observers billions of light-years away. These gravitational waves were predicted by Einstein but remained undetected for a full century, until the exquisitely sensitive instruments of LIGO and Virgo finally captured the whispered vibrations of space-time itself. The first detection in September 2015 was caused by two black holes, each roughly 30 times the mass of our Sun, spiraling together in their final moments before merger. The collision released more energy in gravitational waves than all the stars in the observable universe emit in light, yet the disturbance it created in space-time was so small that it changed the length of LIGO's 4-kilometer arms by less than 1/10,000th the width of a proton. This detection marked not just a triumph of human ingenuity, but a profound moment in our understanding of the cosmos. For the first time, we could listen to the universe rather than just look at it, hearing the deep bass notes of colliding black holes and the higher frequencies of merging neutron stars as they sang their final songs in the language of curved space-time. As we drift through this curved cosmic landscape, we can begin to appreciate how space-time curvature manifests itself in the celestial mechanics we observe every night. The Moon's gentle orbit around Earth is not maintained by invisible strings or mysterious forces, but by the natural curvature that Earth's mass creates in the local space-time geometry. The Moon is simply following the straightest possible path through curved space, a path that happens to be a stable ellipse around our planet. Similarly, Earth's orbit around the Sun represents our planet's natural motion through the curved space-time, created by the Sun's enormous mass. We are not being pulled toward the Sun by some attractive force. We are falling freely through curved space-time, following a path that keeps us in a stable orbit at just the right distance to maintain the gentle temperatures that make life possible. This freefall motion is the same weightless floating that astronauts experience in orbit around Earth. They are not floating because there is no gravity in space. Earth's gravitational influence extends far beyond the International Space Station's altitude. Instead, they float because they are in perfect freefall, following the natural curvature of space-time around Earth just as Earth follows the curvature around the Sun. The beauty of Einstein's geometric understanding of gravity becomes even more apparent when we consider how light behaves in curved space-time. Photons, being massless, cannot be affected by gravity in the Newtonian sense. There is nothing for a gravitational force to pull upon. But light does respond to space-time curvature following the geodesics, the straightest possible paths through whatever geometric landscape it encounters. This is why we observe gravitational lensing, one of the most beautiful confirmations of Einstein's theory. When light from a distant galaxy travels past a massive cluster of galaxies, on its way to our telescopes, the curvature of space-time around the cluster bends the light's path, acting like a cosmic magnifying glass. The distant galaxy appears distorted, sometimes stretched into multiple images or elongated into bright arcs. But these distortions are not flaws in our instruments. They are the signatures of curved space-time itself. Even more remarkably, this gravitational lensing allows us to map the distribution of dark matter in galaxy clusters. Dark matter doesn't emit light and barely interacts with ordinary matter, making it invisible to conventional telescopes. But it does curve space-time, and we can detect this curvature by observing how it affects the paths of light rays from background galaxies. In this way, Einstein's theory gives us a tool for studying the universe's most mysterious component. The fabric of space-time also exhibits more exotic behaviors near extremely massive or dense objects. Around black holes, Space-time curvature becomes so extreme that it creates regions where time itself slows to a crawl. From the perspective of distant observers, near the event horizon, that boundary beyond which nothing can escape, time dilation becomes so severe that processes that would take seconds for someone falling into the black hole would appear to take millennia when viewed from a safe distance. This is not a failure of our clocks or instruments, but a fundamental feature of curved space-time geometry. Time and space are so intimately connected that extreme curvature in space necessarily affects the flow of time. The deeper the gravitational well, the more slowly time flows, creating a cosmic landscape where temporal geography is as varied and dramatic as spatial geography. As we continue our gentle drift through this curved cosmic landscape, we begin to appreciate how Einstein's insights transformed not just our understanding of gravity, but our entire conception of reality itself. Space and time are not the fixed, unchanging backdrop that Newton imagined, but dynamic, flexible aspects of a living universe that responds to every particle of matter and every quantum of energy within it. The implications of this understanding continue to unfold as we explore deeper into the cosmos, revealing new mysteries and new beauties with each observation. In our next chapter, we will focus more closely on how this space-time curvature affects the flow of time itself, creating a gravitational chronography where clocks tick at different rates, depending on their position in the cosmic landscape. Now we float toward one of the most beautiful and practical manifestations of Einstein's curved space-time, the way gravity itself affects the flow of time, creating a cosmic chronography, where temporal rivers run at different speeds depending on their position in the gravitational landscape of the universe. Picture time not as a single, uniform flow, but as a vast network of streams and currents, each influenced by the gravitational wells and hills that massive objects create in space-time. In the deep valleys near massive stars, time flows like a lazy river, each second stretching languidly into the next. On the high plateaus of empty space, far from gravitational influence, time rushes forward like a mountain stream, carrying moments past at its maximum rate. This gravitational time dilation is not a theoretical curiosity, but a measurable reality that affects our daily lives in ways both subtle and profound. Every time you check your location using GPS, you are relying on a network of satellites that must constantly account for the different rates at which time flows at different altitudes above Earth's surface. The GPS satellites orbit approximately 12,500 miles above Earth's surface, where they experience a gravitational field about 4 times weaker than what we feel on the ground. In this reduced gravitational environment, their atomic clocks run faster than identical clocks on Earth's surface, about 45 microseconds faster each day. This might seem like an infinitesimally small difference, but in the precision world of satellite navigation, those microseconds translate to errors of several miles in position calculations. To compensate for this gravitational time dilation, GPS engineers program the satellite clocks to run slightly slow when they are on the ground, so that when they reach their orbital altitude and begin experiencing weaker gravity, they speed up to exactly the right rate. This adjustment happens automatically, invisibly, every moment of every day. As Einstein's century-old insights continue to guide spacecraft through the cosmos with extraordinary precision, but gravitational time dilation extends far beyond the practical realm of satellite navigation. It reveals something profound about the nature of time itself. That temporal flow is not absolute but relative, not uniform but variable, not independent but intimately connected to the gravitational structure of space-time. Imagine standing at the base of a mountain with a friend who climbs to the summit. As your friend ascends, moving further from Earth's center and into regions of slightly weaker gravity, their clocks begin to run faster relative to yours. The difference is tiny, about 1 part in a billion for every 100 feet of altitude, but it is real and measurable with sufficiently precise instruments. This means that your friend on the mountaintop literally ages faster than you do at sea level. Over the course of a lifetime, the difference amounts to only microseconds, but those microseconds represent a fundamental truth about our universe, that time itself is malleable, flexible, responsive to the gravitational environment in which it flows. The effect becomes more dramatic as we venture into stronger gravitational fields. On the surface of the Sun, where gravity is about 28 times stronger than on Earth, time runs about 2 parts per million slower than it does in Earth's gravitational field. This might not sound like much, but over the billions of years of the Sun's lifetime, this time dilation accumulates to significant differences in the rate of aging between objects in different gravitational environments. For neutron stars, those incredibly dense remnants of massive stellar explosions, gravitational time dilation becomes far more pronounced. A neutron star typically contains about 1.4 times the mass of our Sun compressed into a sphere, only about 12 miles across. The surface gravity is so intense that time runs significantly slower there than it does in the weaker gravitational fields of ordinary space. If you could somehow survive on the surface of a neutron star and look out at the rest of the universe, you would see everything happening in fast forward. Stars would appear to evolve more quickly, planets would race through their orbits, and the cosmic dance of galaxies would accelerate to a frantic pace. Meanwhile, observers watching you from a safe distance would see your movements slowed to a crawl, your processes unfolding at what would appear to be a glacial pace. This is not an optical illusion or a trick of perception. It is the literal flow of time responding to the curvature of space-time. In regions of strong gravitational fields, the geometry of space-time is so severely curved that the coordinate we call time stretches and dilates, creating temporal landscapes as varied and dramatic as any geographical terrain. Black holes represent the ultimate extreme of gravitational time dilation. As you approach the event horizon of a black hole, time dilation becomes more and more severe. At the event horizon itself, time appears to stop completely from the perspective of distant observers. This is why, from our safe vantage point far away, objects falling into black holes appear to slow down and fade away as they approach the event horizon, never quite seeming to cross that final boundary. But from the perspective of someone falling into the black hole, time continues to flow normally. They experience no slowing of their personal time, no stretching of their subjective moments. It is only when they look back toward the outside universe that they would see time accelerated to an incredible degree, with the entire future history of the cosmos playing out in fast forward as they cross the event horizon. This creates one of the most poetic paradoxes in physics, that the same event, crossing a black hole's event horizon, appears completely different depending on your frame of reference. From outside, it never quite happens. From inside, it happens normally. Both perspectives are equally valid, equally true, because time itself flows differently in different regions of curved space-time. The implications of gravitational time dilation extend throughout the cosmos. In galaxy clusters, where massive concentrations of dark matter create deep gravitational wells, time flows more slowly than in the vast empty spaces between galaxy clusters. This means that the universe itself ages at different rates in different locations, creating a cosmic chronography where some regions are temporally older than others, even though they came into existence at the same moment during the Big Bang. This variable flow of time also affects how we observe distant astronomical events. Light from objects in strong gravitational fields appears redshifted, its wavelength stretched toward longer, redder colors because the light is climbing out of gravitational wells, where time flows more slowly. This gravitational redshift is distinct from the cosmological redshift, caused by the expansion of space, and it provides another tool for studying the gravitational environment of distant objects. Pulsars, those rotating neutron stars that sweep beams of radiation across space like cosmic lighthouses, provide some of the most precise tests of gravitational time dilation. Their incredibly regular pulses, more accurate than atomic clocks, allow astronomers to detect tiny variations in the flow of time as the pulsars move through different gravitational environments in their orbital motion around companion stars. The binary pulsar system PSOB 1913+16, discovered by Russell Hulse and Joseph Taylor in 1974, has provided decades of precise observations of gravitational time dilation effects. As the two neutron stars orbit each other, their varying distances from each other create cyclical changes in the gravitational time dilation. experienced by each star. These changes affect the observed pulse timing in exactly the way Einstein's theory predicts, providing one of the most stringent tests of general relativity ever performed. Even more remarkably, this system is gradually losing energy by radiating gravitational waves, causing the two neutron stars to spiral slowly closer together. The rate of this orbital decay matches Einstein's predictions with extraordinary precision, providing indirect confirmation of gravitational wave emission, decades before the direct detection by LIGO. As we drift through this contemplation of gravitational time dilation, we begin to appreciate how Einstein's insights reveal time not as the rigid, absolute flow that Newton imagined, but as a dynamic, responsive aspect of reality that dances in harmony with the gravitational structures of the cosmos. Time is not separate from space, not independent of matter and energy, but intimately woven into the very fabric of existence itself. This understanding transforms our perception of temporal experience from something universal and shared to something deeply personal and location-dependent. Your time, flowing at your pace in your gravitational environment, is uniquely yours. The cosmic chronography ensures that no two observers, separated by gravitational differences, ever experience exactly the same temporal flow. Yet this variability in time's passage does not create chaos or disorder. Instead, it creates a beautiful, coherent cosmic symphony where every temporal voice contributes to the overall harmony of space-time. The faster-flowing time in weak gravitational fields balances the slower-flowing time in strong gravitational fields, maintaining the causal structure of the universe and ensuring that the cosmic dance continues with elegant precision. Gently, we discover the most extreme and beautiful manifestation of the cosmic dance between time and gravity, those mysterious objects called black holes where space-time curvature becomes so severe that it creates regions from which not even light can escape and where time itself undergoes the most profound transformations possible in our universe. Black holes are not the violent, destructive monsters that popular imagination often portrays them to be. Instead, they are the universe's most elegant expression of Einstein's geometric vision of gravity regions, where the curvature of space-time has become so pronounced that it creates a new kind of cosmic geography complete with boundaries, horizons, and temporal landscapes unlike anything else in the cosmos. Picture a black hole not as a hole in space, but as the deepest possible gravitational valley in the fabric of space-time. Imagine our familiar trampoline analogy stretched to its ultimate limit, a depression so deep and steep that it creates a well from which nothing can climb out. Once it has fallen past a certain point, this point of no return is called the event horizon, and it represents one of the most profound boundaries in physics. The event horizon is not a physical surface like the boundary of a planet or star. Instead, it is a geometric boundary in space-time itself, a region where the curvature becomes so extreme that all possible paths lead inexorably inward, toward the black hole's center. Once you cross this boundary, every direction you might try to travel, forward, backward, left, right, up, down, leads deeper into the black hole's gravitational embrace. From the perspective of someone far away from the black hole, the event horizon appears as a sphere of perfect blackness, defined not by the absence of matter but by the complete inability of light to escape. Any photon that crosses the event horizon finds itself on a one-way journey toward the black hole's center, unable to return to the outside universe to carry information about what lies beyond that boundary. But perhaps the most beautiful and strange aspect of black holes is how they affect the flow of time itself. As we approach a black hole, gravitational time dilation becomes more and more pronounced, creating temporal effects so dramatic that they fundamentally alter our understanding of simultaneity, causality, and the nature of events themselves. Imagine two astronauts approaching a black hole together, one who will maintain a safe distance, and another who will make the ultimate journey across the event horizon. As the falling astronaut approaches the boundary, time dilation becomes increasingly severe from the perspective of the distant observer. The distant astronaut watches as their companions' clocks slow down, their movements become increasingly languid, and their signals become more and more redshifted. As the falling astronaut approaches the event horizon, they appear to slow to a crawl, their image becoming redder and dimmer until it fades away entirely. From the distant observer's perspective, their companion never quite crosses the event horizon. They appear frozen at the boundary, fading away like a ghost as their light becomes too redshifted to detect. But from the perspective of the falling astronaut, the experience is completely different. Their own time continues to flow normally, their watch ticks at its usual rate, their thoughts proceed at their normal pace, and they experience no slowing or stretching of their personal timeline. As they cross the event horizon, they notice nothing special about that moment. It passes like any other point in their journey, with no fanfare or dramatic transition. What the falling astronaut does notice is that the outside universe appears to speed up dramatically. Looking back toward the distant observer, they see time accelerating to an incredible degree. Stars evolve rapidly, the cosmic microwave background shifts and changes, and the entire future history of the observable universe plays out in fast forward as they fall toward the black hole's center. This creates one of the most profound paradoxes in physics. The same event, crossing the event horizon, appears completely different depending on your frame of reference. Both perspectives are equally valid, equally true, because they represent the genuine flow of time in different regions of severely curved space-time. As the falling astronaut continues their journey beyond the event horizon, they enter a region where the normal relationships between space and time become increasingly exotic. The radial direction toward the black hole's center becomes time-like, meaning that falling inward is as inevitable as moving forward in time. Just as we cannot travel backward in time in normal space-time, nothing inside a black hole can move outward away from the center. The tidal forces near a black hole create another beautifully strange phenomenon, because gravity gets stronger as you get closer to the massive object. There is a difference in gravitational pull between your head and your feet as you fall toward the black hole. For stellar mass black holes, these tidal forces become extreme, stretching objects into long, thin shapes in a process that physicists have whimsically dubbed spaghettification. But this stretching is not a violent tearing apart, it is a gradual, gentle elongation that occurs because different parts of your body experience slightly different gravitational fields. Your feet, being closer to the black hole, experience stronger gravity than your head, causing you to stretch like taffy as you fall. This same tidal effect is what causes ocean tides on Earth, though the Earth-Moon system produces much gentler tidal forces than those found near black holes. For supermassive black holes, those giants that lurk at the centers of galaxies, containing millions or billions of times the mass of our Sun, the tidal forces at the event horizon are actually quite mild. An astronaut could cross the event horizon of a supermassive black hole without experiencing significant stretching, at least initially. The enormous size of these black holes means that the event horizon is very far from the center, and the tidal forces there are surprisingly gentle. Black holes also exhibit a remarkable property called Hawking radiation, named after Stephen Hawking, who showed that quantum mechanical effects near the event horizon cause black holes to slowly evaporate over vast periods of time. This process occurs because quantum fluctuations in the vacuum near the event horizon occasionally create pairs of particles, one of which falls into the black hole while the other escapes to infinity. The escaping particles carry away energy, causing the black hole to slowly lose mass and shrink over time. For stellar mass black holes, this evaporation process is incredibly slow. It would take longer than the current age of the universe for such a black hole to evaporate completely. But smaller black holes evaporate faster, and hypothetical microscopic black holes would disappear in tiny fractions of a second, releasing their mass energy in brilliant flashes of Hawking radiation. This evaporation process creates another beautiful paradox in physics. As a black hole evaporates, its event horizon shrinks, potentially revealing the interior that was previously hidden. But general relativity suggests that information that falls into a black hole is lost forever, while quantum mechanics insists that information must be preserved. This tension, known as the black hole information paradox, remains one of the deepest unsolved problems in physics. The centers of black holes, where general relativity predicts the formation of singularities, points of infinite density and infinite space-time curvature, represent the ultimate limits of our current understanding. At these points, the smooth geometry of space-time breaks down, and our equations lose their predictive power. The singularity is not a place or a thing, but rather a boundary of space-time itself, beyond which our current theories cannot penetrate. Many physicists believe that a complete theory of quantum gravity will eventually resolve the singularity problem, showing that the extreme conditions near a black hole center prevent the formation of true singularities. These quantum effects might create firewalls of intense radiation, or they might cause the black hole interior to connect to other regions of space-time through wormhole-like structures. Black holes also play crucial roles in the large-scale structure and evolution of the universe. The supermassive black holes at the centers of galaxies help regulate star formation by heating and dispersing gas clouds, preventing galaxies from forming stars too rapidly. The jets of high-energy particles that some black holes emit can influence the evolution of entire galaxy clusters, transporting energy across millions of light-years of space. When two black holes spiral together and merge, they create some of the most violent events in the universe, releasing more energy in gravitational waves than all the stars in the observable universe emit in light. These mergers create new black holes with masses equal to the sum of their components, minus the mass energy that was radiated away as gravitational waves during the final moments of their cosmic dance. The detection of these gravitational wave signals by LIGO and Virgo has opened a new window into the universe, allowing us to study black holes directly through their gravitational influence, rather than through the electromagnetic radiation of matter falling into them. Each detection tells us about the masses and spins of the merging black holes, the distance to the event, and the nature of space-time in the most extreme gravitational environments. As we contemplate these cosmic dances from our safe distance between the stars, we can appreciate how black holes represent the ultimate expression of Einstein's vision of gravity as curved space-time. They are not holes in space, but rather the deepest possible valleys in the gravitational landscape, regions where the geometry of reality itself has been transformed by the presence of matter and energy in their most concentrated forms. The cosmic dance between time and gravity reaches its most dramatic expression in these objects, where time dilates to its maximum degree, where space-time curvature becomes extreme, and where the very fabric of reality reveals its most exotic properties. Yet even in their extremity, black holes maintain the elegant mathematical beauty that characterizes Einstein's geometric vision of the universe. Like whispers in the night, the cosmos speaks to us through a variety of phenomena that reveal the intimate relationship between time and gravity on scales both vast and minute. As we drift through the peaceful darkness between stars, we encounter cosmic timepieces, gravitational lighthouses, and ripples in space-time itself that carry messages about the most extreme events in the universe's history. Pulsars, those remarkable rotating neutron stars, serve as the universe's most precise clocks, their lighthouse beams of radiation sweeping across space with a regularity that rivals the best atomic timepieces humans have ever constructed. These stellar remnants, born from the collapse of massive stars, compress more mass than our Sun into spheres only about 12 miles across, creating gravitational fields so intense that they warp space-time in measurable ways. Picture a pulsar as a cosmic lighthouse, its intense magnetic field channeling radiation into narrow beams that sweep across space. As the neutron star rotates, when one of these beams points toward Earth, we detect a brief pulse of radio waves, X-rays, or gamma rays. The Crab pulsar, born from a supernova explosion witnessed by Chinese astronomers in 1054 AD, rotates 30 times per second, creating a strobe-like beacon that has been flashing with metronomic precision for nearly 1,000 years. But these cosmic timepieces do more than just mark the passage of seconds. They reveal how gravity affects the flow of time in the most extreme environments. Binary pulsars, systems where two neutron stars orbit each other in gravitational ballet, provide natural laboratories for testing Einstein's theories with extraordinary precision. The famous Hull-Stainer binary pulsar, designated PSRB 1913+16, consists of two neutron stars orbiting each other once every 7.75 hours. As these incredibly dense objects dance around their common center of mass, They experience varying gravitational fields that cause predictable changes in their orbital period. Due to time dilation effects, when the two neutron stars are closest together in their elliptical orbit, they experience stronger mutual gravitational fields, causing time to flow more slowly. When they are furthest apart, the gravitational time dilation is reduced, and time flows more quickly. These variations in temporal flow create tiny but measurable changes in the arrival times of the pulsar S radio signals, changes that match Einstein's predictions with remarkable accuracy. Even more remarkably, this binary system is slowly losing energy by radiating gravitational waves, causing the two neutron stars to spiral gradually closer together. Over the decades since its discovery, astronomers have measured this orbital decay with extraordinary precision, finding that it matches Einstein's predictions for gravitational wave emission to within a fraction of a percent. This orbital decay represents one of the most beautiful confirmations of Einstein's theory. The two neutron stars are literally dancing themselves to death, their orbital energy being carried away by ripples in space-time itself. In about 300 million years, they will spiral together in a final, catastrophic merger that will create either a more massive neutron star or a black hole, while simultaneously releasing a tremendous burst of gravitational waves and electromagnetic radiation. Gravitational waves themselves represent perhaps the most direct manifestation of the dynamic relationship between time and gravity. These ripples in spacetime predicted by Einstein but not directly detected until 2015 carry information about the most violent events in the cosmos, colliding black holes, merging neutron stars, and possibly even echoes from the birth of the universe itself. The first gravitational wave detection by LIGO, designated GW150914, was caused by the merger of two black holes approximately 1.3 billion light-years away. Each black hole was roughly 30 times more massive than our Sun, and when they finally collided, after eons of spiraling together, they converted about 3 solar masses of matter into pure gravitational wave energy in less than a second. This energy release was staggering. For a brief moment, the collision produced more power in gravitational waves than all the stars in the observable universe emit in light. Yet the effect on space-time at Earth was incredibly subtle, changing the length of LIGO's 4-kilometer arms by less than 1/10,000th the width of a proton. This detection required instruments of almost unimaginable sensitivity, capable of measuring changes in distance smaller than the size of atomic nuclei. The gravitational waves from this collision carried with them information about the nature of space-time itself. As the waves propagated across the cosmos at the speed of light, they alternately stretched and compressed space in directions perpendicular to their motion, creating a characteristic chirp pattern as the two black holes spiraled faster and faster together before their final merger. But gravitational waves do more than just confirm Einstein's century-old predictions. They open an entirely new window for observing the universe. Unlike electromagnetic radiation, which can be absorbed, scattered, or blocked by intervening matter, gravitational waves pass through everything virtually unimpeded, carrying pristine information from the most violent and exotic events in cosmic history. The cosmic microwave background, that faint afterglow of the Big Bang that fills all of space, provides another window into the relationship between time and gravity on cosmological scales. This ancient light, released when the universe was only 380,000 years old and had cooled enough for atoms to form, carries imprinted within it tiny fluctuations that reveal the gravitational structure of the early universe. These fluctuations, detected with exquisite precision by satellites like the Cosmic Microwave Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe WMAP, and the Planck Observatory, show us how matter was distributed when the universe was still young and hot. The slightly denser regions revealed by these temperature variations would eventually grow, under the influence of gravity, into the galaxies and galaxy clusters we see today. But the cosmic microwave background also preserves information about how time itself flowed. In the early universe, the precise pattern of fluctuations depends on the interplay between matter, radiation, and gravity during the first few 100,000 years after the Big Bang, when the universe was expanding. and cooling according to the dynamics of curved spacetime on a cosmic scale. Neutron stars, beyond their role as pulsars, represent some of the most extreme laboratories for studying gravitational time dilation. The surface gravity of a typical neutron star is about 200 billion times stronger than Earth's gravity, creating time dilation effects that are significant even by cosmic standards. On the surface of a neutron star, time flows about 30% more slowly than it does in the weak gravitational field of interstellar space. This means that processes that would take seconds on a neutron star's surface would appear to take nearly 2 seconds when viewed from a distant reference frame. This time dilation affects everything from the neutron star's rotation rate to the frequency of radiation emitted from its surface. The magnetic fields of neutron stars can be trillions of times stronger than Earth's magnetic field, and these intense magnetic environments interact with the curved spacetime around the neutron star in fascinating ways. Charged particles spiraling in these magnetic fields emit radiation that is affected by both the gravitational time dilation and the Doppler shifts caused by the neutron star's rapid rotation. Some neutron stars, called magnetars, have magnetic fields so intense that they can affect the very structure of spacetime around them. These objects occasionally release tremendous bursts of X-rays and gamma rays, events so powerful that they can briefly outshine entire galaxies. The energy for these outbursts comes from the gradual decay of the magnetar's magnetic field, which releases stored magnetic energy in sudden, violent reconnection events. White dwarf stars, the cooling remnants of stars like our Sun, provide gentler examples of gravitational time dilation in action. These Earth-sized objects contain about as much mass as the Sun, creating surface gravitational fields about 100,000 times stronger than Earth's. While this is far less extreme than neutron star gravity, it is still sufficient to create measurable time dilation effects. The light emitted by white dwarf stars is gravitationally redshifted as it climbs out of the star's gravitational well, providing direct observational evidence of gravitational time dilation. This redshift is distinct from the Doppler redshift caused by the star's motion through space, and careful spectroscopic measurements can separate these two effects. To test Einstein's predictions, binary star systems containing white dwarfs often show dramatic time-dependent phenomena, as matter flows from a normal companion star onto the dense white dwarf surface. This infalling matter forms an accretion disk that spirals inward under the influence of gravity, heating up and glowing brightly as gravitational potential energy is converted to thermal energy. The time scales of these accretion processes are governed by the interplay between gravity and the other fundamental forces, creating complex temporal patterns in the system's brightness. Some systems show regular outbursts as matter accumulates on the white dwarf surface and then ignites in thermonuclear explosions called novae, while others show more chaotic variations as the accretion rate fluctuates. As we contemplate these cosmic phenomena from our peaceful vantage point between the stars, we can appreciate how the universe speaks to us in whispers, the gentle pulse of distant pulsars, the subtle chirp of gravitational waves, the faint glow of the cosmic microwave background, and the patient redshift of starlight climbing out of gravitational wells. Each of these phenomena carries within it information about the fundamental relationship between time and gravity, revealing aspects of Einstein's curved spacetime that we could never discover through earthbound experiments alone. The cosmos itself serves as our laboratory, providing natural experiments of such scale and precision that they continue to test and confirm our understanding of reality's deepest principles. These temporal whispers from across the universe remind us that we are not separate observers of cosmic phenomena, but participants in the same space-time fabric that governs the motion of galaxies and the flow of time itself. The gravitational waves that pass through our bodies, the cosmic microwave background photons that strike our eyes, and the light from distant pulsars that reaches our telescopes all connect us directly to the cosmic dance between time and gravity that shapes everything in existence. In the quiet space of cosmic expansion, we find ourselves contemplating the grandest temporal story ever told, the evolution of time itself across the observable universe. From the first moments after the Big Bang to the distant future when stars will fade and time will flow in ways we can barely imagine. The universe began not with an explosion in space, but as an expansion of space itself, carrying time along with it in a cosmic dance that has been unfolding for 13.8 billion years. In those first moments when the universe was smaller than an atom and hotter than the core of any star, time and space emerged together from a quantum foam of pure possibility, setting the stage for everything that would follow. During the earliest fraction of a second, the universe underwent a period of exponential expansion called cosmic inflation, when space itself stretched faster than the speed of light, carrying with it the primordial fluctuations that would eventually grow into galaxies and stars. This inflationary epoch lasted only about 10 to 30 seconds, but during that brief interval, the universe expanded by a factor of at least 1026, transforming quantum fluctuations into the seeds of cosmic structure. As the universe expanded and cooled, the fundamental forces that govern the cosmic dance began to separate from their unified state. First gravity, then the strong nuclear force, then the electromagnetic and weak forces distinguished themselves, each taking on its modern character and beginning to shape the evolution of matter and energy in distinctive ways. The expansion of space itself creates one of the most beautiful and profound aspects of cosmic time, the relationship between distance and look-back time. That allows us to observe the universe as history directly. When we look at distant galaxies, we see them not as they are now, but as they were when their light began its journey to us, across billions of years of expanding space. The most distant galaxies we can observe appear as they were, when the universe was only a few 100 million years old, still in its cosmic childhood. These primordial galaxies show us a universe very different from today's, smaller, denser, more chaotic, filled with the first generation of stars that began the long process of forging heavy elements in their nuclear furnaces. As we look deeper into space and further back in time, we eventually reach the cosmic microwave background, that faint afterglow of the Big Bang that represents the earliest light in the universe. This radiation comes from a time when the universe was only 380,000 years old and had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely through space for the first time. Before this epoch of recombination, the universe was opaque to light, filled with a hot plasma of charged particles that absorbed and scattered photons. Before they could travel far, the cosmic microwave background represents the surface of last scattering, the moment when the universe became transparent and light began its cosmic journey to our telescopes. But the expansion of space affects not just our ability to observe distant objects. It also influences the flow of time itself on cosmic scales. As the universe expands, the average density of matter decreases, weakening the overall gravitational field that pervades the cosmos. This gradual weakening of cosmic gravity causes time to flow slightly faster now than it did in the early universe when matter was more densely packed. This effect is incredibly subtle. The change in the flow of time due to cosmic expansion amounts to only a few parts per billion over the entire age of the universe, but it is real and measurable. Another manifestation of the intimate relationship between gravity and time that Einstein revealed through his theory of general relativity. The expansion of space also stretches the wavelengths of photons as they travel across cosmic distances, creating the cosmological redshift that we observe in the spectra of distant galaxies. This redshift is not caused by the motion of galaxies through space, but by the expansion of space itself, which stretches the wavelengths of light just as it stretches the distances between galaxies. The relationship between redshift and distance, first observed by Edwin Hubble in the 1920s, revealed that the universe is expanding uniformly in all directions. More distant galaxies show greater redshifts, indicating that they are receding from us at higher speeds. This observation provided the first direct evidence for the Big Bang theory and established our modern understanding of cosmic evolution. But the expansion of the universe is not slowing down, as we might expect from the gravitational attraction of matter. Instead, it is accelerating, driven by a mysterious component called dark energy that makes up about 68% of the universe's total energy density. This dark energy acts like a repulsive force, pushing space apart and causing the expansion to speed up over time. the discovery of cosmic acceleration. Announced in 1998 and honored with the 2011 Nobel Prize in Physics, came from observations of distant Type Ia supernovae, stellar explosions that serve as standard candles for measuring cosmic distances. These supernovae appeared dimmer than expected in an expanding but decelerating universe, indicating that cosmic expansion has been accelerating for the past several billion years. This acceleration has profound implications for the future evolution of time and space in the universe. If dark energy continues to dominate cosmic dynamics, the universe will expand exponentially, eventually reaching a state where space stretches so rapidly that light from distant objects can never reach us. Galaxies beyond our local group will disappear beyond the cosmic horizon, leaving our descendants in an increasingly empty and isolated universe. But even as the universe expands and accelerates, gravity continues to play its role in shaping cosmic structure. Dark matter, which makes up about 27% of the universe's energy density, provides the gravitational scaffolding upon which galaxies and galaxy clusters form. This invisible matter interacts only through gravity, revealing its presence through its gravitational effects on visible matter and light. The large-scale structure of the universe, the cosmic web of filaments and voids that connects galaxies across billions of light years, represents gravity's triumph over expansion on local scales. While space expands uniformly on the largest scales, gravity has pulled matter together into increasingly complex structures. From the first small fluctuations in the early universe to the vast galaxy clusters we observe today, this ongoing battle between expansion and gravity creates a temporal hierarchy in cosmic evolution. On the largest scales, expansion dominates, carrying galaxy clusters apart and eventually leading to the heat death of the universe. On intermediate scales, gravity wins, pulling matter together into galaxies and stars. On the smallest scales, other forces take over, electromagnetic forces holding atoms together, nuclear forces powering stellar fusion, and quantum forces governing the behavior of fundamental particles. Star formation represents one of the most beautiful chapters in the universe's temporal story. As gravity pulls together clouds of gas and dust, the material heats up and eventually ignites nuclear fusion, creating new stars that burn for millions or billions of years. These stellar furnaces forge heavy elements in their cores, enriching the cosmos with the carbon, oxygen, silicon, and iron that make planets and life possible. The life cycle of stars follows different temporal patterns depending on their mass. Massive stars burn bright and die young, exploding as supernovae after only millions of years and leaving behind neutron stars. Or black holes, low-mass stars like our Sun burn more slowly and steadily, living for billions of years before gently shedding their outer layers and cooling as white dwarfs. The most massive stars end their lives in the most dramatic fashion, collapsing into black holes that represent the ultimate extreme of gravitational time dilation. As these stellar remnants accumulate matter and merge with other black holes, they grow larger and more massive, creating ever deeper wells in the fabric of space-time. Eventually, if current theories are correct, even black holes will evaporate through Hawking radiation, returning their mass energy to the cosmos in the form of elementary particles and radiation. This process takes an unimaginably long time. A solar mass black hole would take about 1,067 years to evaporate completely, far longer than the current age of the universe. As we contemplate this vast temporal panorama from our peaceful vantage point between the stars, we can appreciate how the cosmic dance between time and gravity plays out on every scale. From the quantum fluctuations of the early universe to the heat death that awaits in the far future, each epoch of cosmic history has its own characteristic time scales, its own gravitational dynamics, and its own unique relationship between matter, energy, space, and time. The story of cosmic time is also the story of increasing complexity and organization. From the simple hydrogen and helium of the early universe, gravity and nuclear processes have created an increasingly rich tapestry of elements, molecules, planets, and possibly life. The same gravitational forces that shape the large-scale structure of the universe also enable the formation of solar systems where complex chemistry and biology can flourish. Yet this increasing complexity is temporary in cosmic terms. The acceleration of cosmic expansion, driven by dark energy, will eventually separate all structures beyond our local gravitational group. Stars will exhaust their nuclear fuel, galaxies will fade, and the universe will enter a long, cold epoch where time flows through an increasingly empty and dark cosmos. But even in this distant future, the fundamental relationship between time and gravity will persist. Space will continue to expand, carrying with it the curved geometry that massive objects create in space-time. Time will continue to flow at different rates in different gravitational environments, maintaining the elegant mathematical relationships that Einstein discovered and that govern the cosmic dance on all scales. As our journey through the cosmic dance between time and gravity draws toward its peaceful conclusion, we find ourselves floating in the gentle darkness between stars, surrounded by the whispered messages that gravitational waves carry across billions of years, bathed in the ancient light of the cosmic microwave background, and moving through space-time at our own unique temporal pace in this vast, expanding, evolving universe that we are privileged to call home. As we drift gently back from our cosmic journey through the vast temporal landscapes of the universe, we find ourselves changed by what we have witnessed, the elegant dance between time and gravity, that shapes everything from the smallest quantum fluctuations to the largest structures in the cosmos, from the briefest moments after the Big Bang to the distant future when stars will fade and time itself will flow through an increasingly empty cosmos. We have seen how time, which once seemed like an absolute river, flowing uniformly throughout the universe, is actually a flexible aspect of space-time that responds to the presence of matter and energy, stretching near massive objects, dilating in strong gravitational fields, and even stopping completely at the event horizons of black holes. We have learned that gravity itself is not a force pulling objects together, but the curvature of space-time geometry, guiding the motion of everything from photons to galaxies along the straightest possible paths through the curved landscape of reality. Throughout our journey, we have encountered the universe's most precise timekeepers, pulsars that flash with metronomic regularity, gravitational waves that carry temporal messages across billions of light years, and the cosmic microwave background that preserves information about time's flow. In the early universe, each phenomenon has whispered to us about the intimate relationship between temporal flow and gravitational curvature, revealing aspects of Einstein's geometric vision that continue to amaze and inspire us more than a century after his revolutionary insights. The cosmic dance between time and gravity unfolds on every scale we can imagine. In the quantum foam of space-time itself, virtual particles pop into existence and annihilate in intervals so brief that they barely qualify as moments. In stellar cores, nuclear fusion proceeds at rates governed by both quantum mechanics and general relativity, creating the elements that make planets and life possible. In galaxy clusters, dark matter and dark energy engage in a gentle tug-of-war that determines whether cosmic structures will continue to grow or eventually be torn apart by accelerating expansion. We have learned that our everyday experience of time, the steady tick of clocks, the regular progression from past to future, the synchronized flow of temporal experience that we share with others around us, is actually a very special case that applies only in weak gravitational fields and at slow speeds. The deeper reality is far more beautiful and strange, with time flowing at different rates, in different locations, past and future mixing in complex ways near extreme gravitational sources, and the very fabric of space-time rippling with waves that carry information about the most violent events in cosmic history. Yet despite its strangeness, this deeper reality maintains a profound mathematical elegance and internal consistency that speaks to something fundamental about the nature of existence itself. The same equations that describe the gentle precession of Mercury's orbit also predict the existence of black holes, gravitational waves, and the expansion of the universe. The geometric relationships that govern time dilation in GPS satellites also explain the redshift of light from distant galaxies and the gravitational lensing of background objects by intervening mass concentrations. As we float here in the peaceful darkness between stars, we can feel our connection to this cosmic dance. The gravitational waves from colliding black holes pass through our bodies, stretching and compressing our atoms by imperceptible amounts. The expansion of space itself carries us along with the general flow of cosmic evolution. The curvature of space-time around Earth affects the flow of time in our location, connecting us intimately to the same geometric relationships that govern the motion of planets and the evolution of galaxies. This connection extends beyond the purely physical, to touch something deeper about our place in the universe. We are not separate observers of cosmic phenomena, but participants in the same space-time fabric that connects everything in existence. The carbon in our bodies was forged in stellar cores where time flowed differently than it does on Earth. The oxygen we breathe was created in supernovae, whose gravitational collapse created ripples in space-time that still echo across the cosmos. The cosmic dance between time and gravity also reveals something profound about the nature of knowledge and discovery. Einstein's insights came not from expensive experiments or complex instruments, but from careful thought, mathematical reasoning, and a willingness to question assumptions that seemed obviously true. The same intellectual tools that revealed the geometric nature of gravity continue to guide our exploration of quantum mechanics, cosmology, and the search for a unified understanding of all fundamental forces. As we contemplate the vast temporal vistas we have explored, from the Planck time of 10 to 43 seconds, when quantum effects dominated the early universe, to the 10,100 years it may take for the last black holes to evaporate through Hawking radiation, we gain perspective on our own brief lives and the short history of human civilization. Yet this perspective brings not insignificance but wonder, not loneliness but connection to something infinitely larger and more beautiful than we might have imagined. The dance continues all around us, in every moment and at every scale. Atoms in our bodies follow geodesics through the curved space-time around Earth. Light from distant galaxies carries information about cosmic evolution encoded in its redshift and travel time. The GPS signals we use for navigation are continuously corrected for relativistic effects that reflect the fundamental relationship between time and gravity. Future generations will undoubtedly discover new aspects of this cosmic dance that we cannot yet imagine. Quantum gravity may reveal how space-time itself emerges from more fundamental structures. New observations may uncover the nature of dark matter and dark energy, those mysterious components that dominate cosmic evolution, but remain invisible to our current instruments. Advanced civilizations may learn to manipulate space-time curvature directly, creating technologies that seem impossible from our current perspective. But the fundamental beauty of the relationship between time and gravity will endure, continuing to inspire wonder and guide discovery. As long as conscious beings exist to contemplate the cosmos, the elegant mathematical relationships that Einstein discovered, the geometric vision of curved space-time, and the deep connections between matter, energy, space, and time represent truths about reality that transcend any particular species or civilization. As our gentle journey draws to its close, we carry with us a new appreciation for the subtle beauty that surrounds us in every moment. Time flows past us like a cosmic river, carrying us forward through the curved space-time geography of our solar system, our galaxy, and the larger universe beyond. Gravity holds us gently to our planet while simultaneously guiding the planet through its orbital dance around the Sun, which itself moves through the gravitational landscape of the Milky Way galaxy. In this vast cosmic choreography, every particle, every planet, every star, and every galaxy follows the most natural possible paths through the curved geometry of existence. There is no force pushing or pulling, no external choreographer directing the dance, only the elegant mathematical relationships between matter, energy, space, and time that create the most beautiful ballet in all of existence. The stars above us continue their ancient burning, marking cosmic time with their steady nuclear processes. The galaxies beyond slowly spiral through their evolutionary dances, carried apart by cosmic expansion while held together by the gravitational bonds that connect their billions of stars. And throughout it all, time flows in its myriad streams, fast in empty space, slow near massive objects, stopped at event horizons, and stretched across the expanding cosmos in patterns of exquisite mathematical beauty. As we rest here in the gentle embrace of curved space-time, feeling the peaceful flow of time carrying us forward into an uncertain but wondrous future. We can take comfort in knowing that we are part of something infinitely larger than ourselves, participants in the cosmic dance between time and gravity that began with the Big Bang, and will continue until the last black hole evaporates into the quantum vacuum, leaving only the whispered memory of when matter and energy once danced together in the curved space-time of a young and vigorous universe. Good night from the sleepy scientist.